Pluto was once regarded as a legitimate planet in the solar system. It is still a dwarf planet that captivates and eludes explanation. Despite its proximity to Earth, its previous classification, and the most recent bold assertions made by well-known astrophysicists Michio Kaku and Neil deGrasse Tyson have sparked new interest in Pluto. They have suggested that Pluto, an ice-covered planet, could be heading in the direction of a devastating encounter with Neptune, triggering a flurry of inquiries regarding the consequences and plausibility of such an event. Could this scenario result in an exaggerated theory, or is there proper cause for concern? Let's investigate the potential consequences of an initial Pluto-Neptune collision. Pluto was classified as a planet due to its reclassification as a dwarf planet. Its erratic orbit has maintained it as a topic of ongoing discussion in the world of astronomy. The most recent leading scientific studies suggest that Pluto's orbital course poses a danger, coinciding with Neptune's. This sounds alarming. Concerning the possibility of a fatal impact because of their proximity in respective orbits, can a collision actually happen between Neptune and Pluto? And if so, what would the implications be for Pluto's orbit? There is nothing like the Sun in our solar system. Pluto's orbit spans an intricate 248 years, which means that since its discovery in 1930, Pluto hasn't even completed one full orbit yet. However, the peculiarity of Pluto's orbit doesn't end there. It continues with a deviating elliptical path, substantially different from the nearly circular orbits of the majority of other planets. To advance, Pluto's orbit makes matters more difficult, tilted 17 degrees toward the ecliptic, resulting in an inclination much steeper than that of other planetary routes. The fascinating aspect of Pluto's orbit is its relationship with Neptune's. Approximately every 20 years, during each of Pluto's prolonged orbits, it gets closer to a strange anomaly between the Sun and Neptune, in contrast to their usual positions. This pair of planets in our solar system raises the crucial question: why have Pluto and Neptune not yet collided? The answer lies in the powerful forces of gravity exerted by other celestial bodies. After Pluto was discovered in the solar system, astronomers quickly acknowledged the peculiarity of its orbit. In contrast to the almost flat orbits of the other planets, Pluto's steep angle and elliptical trajectory were clearly different. The degree of difficulty of its path became even more evident as researchers realized that Neptune's orbit crosses that of Pluto, despite these unconventional features. The orbit of Pluto has remained remarkably stable as a result of the gravitational effects of other celestial bodies. The problem of three-body celestial mechanics aims to provide an explanation for the interactions and movements of three bodies, such as Pluto, Neptune, and the Sun. Pluto's path through space can be erratic. Even the smallest changes in initial circumstances can have drastic effects on its long-term trajectory. However, simulations have demonstrated that Pluto's orbit has remained constant over long timescales, indicating that its path is not as chaotic as it may appear at first. The significant gravitational pull from Jupiter and other massive bodies plays a crucial role in keeping Pluto's orbit stable. These forces have been essential in maintaining the overall order of our solar system and preventing any potential chaos for billions of years, while Pluto's orbit demonstrates a fascinating equilibrium between order and chaos. It's important to acknowledge the inherent difficulties in predicting how celestial bodies move, especially those with irregular orbits. Despite numerical simulations providing valuable insights, they also emphasize space's unpredictable nature. Events that predict the future remain uncertain. The issue brought up by astrophysicists like Tyson and Kaku about the possibility of a collision between Neptune and Pluto may appear remote. However, their cautions have caught the public's attention. If such a collision were to happen, the results could be detrimental to our solar system. The impact would release a massive amount of energy, most likely responsible for Pluto's destruction due to its small size and icy composition. The resulting debris could pose a significant risk to nearby planets and their moons, including Earth. The effects of a collision between Pluto and Neptune would extend beyond Pluto alone. For Neptune, the collision could significantly alter its atmosphere and orbit, depending on the nature of the incident. Michio Kaku, an acclaimed theoretical physicist, offers a unique perspective on the subject at hand. His extensive research into string theory and celestial mechanics suggests that getting a handle on Pluto's orbit could lead to valuable insights into the physics regulating space exploration. By studying the gravitational interactions shaping Pluto's orbit, we can acquire crucial knowledge for future space missions. This science could benefit more from knowledge. It's preparing for potential threats from space and assisting in the exploration of far-off regions of the solar system and beyond. The principles derived from Pluto's orbit also have wider implications. For research into other dwarf planets and trans-Neptunian objects, Pluto's complicated orbit challenges our comprehension of how planets move, pointing out how much more unpredictable and dynamic the universe is than we frequently comprehend. The relationship between string theory and the mechanics of the universe emphasizes the significance of understanding how Pluto and other celestial bodies interact. In the event of a collision between Neptune and Pluto, it would be a landmark event in cosmology, offering a rare chance to investigate string theories under the extreme conditions that would result from such a collision. A lot of energy in the potential behavior of basic particles and major forces at high energy levels, the main focus of string theory could be observed. Despite the impact on Earth probably being minimal due to our distance from the outer solar system, the broader scientific repercussions would be profound. Such a collision would provide new opportunities to learn about the fundamental nature of the universe, especially in areas involving string theory and theoretical physics. Pluto's unusual orbit continues to captivate the imaginations of both space enthusiasts and astronomers. The ongoing debate over its status as a dwarf planet has reinvigorated interest in its role within our solar system. The concerns raised by Tyson and Kaku underscore the complex forces that control how celestial bodies move, highlighting the significance of understanding the effects of gravity and orbital mechanics. These forces are important for understanding the dynamics of our solar system and the ongoing discussion concerning Pluto's status as a dwarf planet. Pluto's steep and elliptical orbit defies conventional theories of planetary motion. In contrast to the nearly circular paths followed by other nearby planets, Pluto's orbit crosses Neptune's at certain points during its long journey around the Sun. The forces of gravity exerted by planets like Neptune and others have played an important role in keeping Pluto's orbit relatively enduring throughout the centuries. Despite this, predicting how celestial bodies will act in the future remains a challenging and unpredictable task. The possibility of a collision between Pluto and Neptune serves as a reminder of the inherent uncertainties in planetary dynamics. Although such an event appears extremely remote in the near future, gravitational interactions between Neptune and Pluto illustrate the delicate balance that exists within our solar system. The study of Pluto's orbit offers crucial lessons for future space missions, assisting researchers in exploring other distant bodies and attaining a more in-depth comprehension of planetary evolution. NASA's New Horizons mission began with groundbreaking photographs and data of Pluto and its moons during its historic flyby in 2015. This mission disclosed fascinating information about Pluto's surface, including large expanses of water ice and frozen nitrogen plains, enhancing our understanding of the processes that shape this distant world. The success of the New Horizons mission emphasized the technological advancements and concerted efforts required to visit the farthest reaches of our solar system. Our solar system, through Pluto research and its moons, gave scientists invaluable information. Insights into the variety of the heavens, conditions, and bodies found in the outermost parts of the solar system. These findings have significant applications. For upcoming missions, investigate additional distant dwarf planets and trans-Neptunian objects that scientists can use with additional information. Regarding the planet formation and evolution, Pluto's transformation into a dwarf planet has sparked significant discussions regarding the within our we define celestial bodies. A solar system that reflects a larger concerns regarding scientific classification and the nature of change of our knowledge of astronomy. Understanding Pluto's orbit is crucial. Insights into the mechanics of space and planets' dynamics, particularly as we venture further out into the wilderness of the solar system. By exploring Pluto's interactions with other planets and Neptune's celestial objects, we continue to expand our understanding of the formation and Pluto's development of planetary systems, discoveries, and ongoing research substantially contributed to our understanding of planetary motion, and the development of a region known as the Kuiper Belt beyond Neptune, were tiny icebergs. Bodies that comprehend Pluto's orbit provides useful information about the gravitational interactions that may have shaped the early offering of the solar system. Essential data for the future of space missions, focused on exploring potentially habitable worlds outside of our solar system, despite the possibility remains of a Pluto-Neptune collision. Extremely low, the study of these objects from outer space serve as a reminder due to the constant nature of the universe as we proceed to investigate the farthest parts of our solar system and beyond. The study of the orbits of planets and celestial mechanics will continue to be important. To our exploration efforts, Pluto's unique orbit provides instructive examples about the complexities of planetary, the forces that shape motion and celestial bodies over time, the continued exploration of Pluto's orbit and its interactions with Neptune serves as a reminder of the unpredictability of the universe. With each new discovery and theoretical model, we expand our comprehension of the universe and advancement. Insights into the mysteries of distant worlds. The study of Pluto's orbit not only provides answers about this distant world, but also aids in our future forecasting trends in celestial behavior. It's contributing to a better understanding of the factors that control our solar system, and beyond. And finally, the possibility of a collision between Pluto and Neptune, despite being highly unlikely, highlights the study of the universe's dynamic nature of Pluto's orbit, its interactions with Neptune, and the gravitational forces at play offer valuable insights into celestial mechanics as we continue to investigate these far-off objects. We refine our planetary systems models and enhance our capacity for forecasting the future cosmic events. The potential for discoveries in this field is limitless. Additionally, as technology advances, so will our capacity to comprehend and study the vast, ever-changing cosmos. The exploration of Pluto's position in the orbit and our solar system will continue to understanding of the universe for years to come. Pluto's orbital behavior, with its distinctive interactions with Neptune, has long been a subject of fascination, and the scientific community's fascination, despite the fact that it is a dwarf Pluto. A planet continues to pose a challenge to comprehension of the dynamics of the planet. Fact that Pluto's orbit intersects Neptune is absent at various points, causing a collision, demonstrates the complex nature of gravitational mechanics in our solar system. One of the most fascinating aspects of this planet's resonance with Neptune is its orbit. Resonance, also known as a 3:2 orbital resonance, indicates that each Pluto completes its orbit around the Sun. Neptune completes to this carefully. The synchronized relationship guarantees the two bodies never come too close to even though they crossed paths with one another. Pluto and Neptune are resonant here. It's basically enmeshed in a cosmic dance where they have their orbits set in such a way that they will never meet in a way like this. The gravitational relationship excellent illustration of the accuracy and balance in the heavens and earth mechanics. The forces that are produced by Pluto's gravity and that of Neptune, vice versa, collaborate to keep things stable orbit. Without this resonance for both, Pluto's orbit could have been disrupted, potentially leading to a collision or additional significant changes in its trajectory. Appreciating this, astronomers rely heavily on interaction, because it sheds light on how celestial bodies can maintain stability even when their paths seem chaotic. Additionally, at first glance, the Kuiper Belt region beyond Neptune is a treasure trove of dwarf planets and icy bodies. The largest known object is Pluto. The orbit of this belt provides useful information regarding the circumstances that prevail in this faraway. The Kuiper Belt is a region of the solar system. Objects, KBOs, and transnunian objects. The TNOs are solar system remnant system, and their study allows us to peek into the circumstances that prevailed during the development of our solar system billions of years ago. Space agencies. Missions are now being directed by organizations like NASA toward investigating these far-flung regions. The goal of NASA's New Horizons, which conducted a flyby of Pluto in 2015, provided us with previously unseen images, information about the surface of Pluto and atmosphere. The mission's findings revealed towering frozen nitrogen plains, mountains of ice, and a variety of weather system that suggests Pluto is a geologically active world. It also showed the diversity of the dwarf planet moons, revealing clues about the formation of moons and the new will emerge in the outer solar system. The mission of Horizon also demonstrated the expanding capabilities of contemporary space exploration. Such missions not only expand our knowledge of distant Pluto-like celestial objects, but they also pave the way for more ambitious research into the Kuiper Belt and beyond. The mission's accomplishment has rekindled interest in exploration. These faraway regions may elicit similar tasks from other objects within the belt, despite that Pluto's orbit appears to be stable, tilted in eccentric trajectory as well. Raises concerns regarding the long run, the fact that the solar system's dynamics, that Pluto's orbit differs so greatly from the nearly circular orbits of the 8 major planets, offers astronomers an engrossing puzzle. For the inclined and elliptical nature of Pluto's orbit serves as an indication that our solar system doesn't work as well as it could seem at first glance. The chaotic behavior that Pluto's orbit demonstrates could have profound implications for our comprehension of the formation of planets and evolution.